assuming it lets me. Okay, cool. Hopefully you can see my screen, and you can probably see my video as well, if that matters. So we're talking about 3-ethyl pentane, which is actually very similar to the structure from chapter 19, which was 3-methyl pentane. So there's 3-ethyl pentane. I've drawn it kind of in a pinwheel. It's very symmetrical. It's actually got what we call a C3 axis of symmetry. If you rotate this thing 3 times in 360 degrees, it becomes the same molecule, right? So you've got a 3-fold symmetry axis. So 3-ethyl pentane has a total of 7 carbons, 5 in the main chain and then in the ring. So it's C7H16 because it's a saturated hydrocarbon, which is always Cn and then H2 times N plus 2. So hydrogen. That adds up to the total of 16. So statistically, if every time, right, we would expect the primary to secondary to tertiary ratio to be 9 to 6 to 1. But the relative reactivities for primary, secondary, and tertiary for bromine are 1 to 80 to 1700. So the tertiary is much more selective. There are 6 times as many secondary hydrogens as there are tertiary, but the tertiary is more than 6 times as reactive. Right? But the secondary is 80 times as reactive. So we're going to want to multiply those together to get our observed ratio, which will then be 9 to 480 to 1700. So the major product is the tertiary product, even though there's only one of those hydrogens, just because it's so much more reactive. So we would expect that the primary product that we're going to get is this one, which is the 3-bromo 3-ethyl pentane, rather than the other 2 possibilities, which are the 1-bromo and 2-bromo. Right, so that's 1-bromo 3-ethyl pentane, and then the third product, the secondary product, would be 2-bromo secondary. This one's the primary, that one's the tertiary. This molecule happens to be one where the number of the position where the bromine is sitting is the same as the primary, secondary, or tertiary, but that's not normal. I mean, it's quite likely that that's not going to be true. So then if we want to do the same thing for the chlorination, right, we still have the same statistical likelihood of 9 to 6 to 1 of the types of hydrogen, but now the relative reactivities, instead of being 1 to 80 to 1700, are 1 to 4 to 5. So we expect our observed ratio to be 9 to 24 to 5. And we've got a different major product, right? The major product is now the 2-chloro 3-ethyl pentane. So what we're looking at is, right, there's a 6 to 1 ratio of secondary to tertiary hydrogens. In the case of bromine, 1700 over 80 is far more than 6 to 1. But in the case of chlorine, 5 over 4 is only 1.25 to 1. So the fact that there are 6 times as many hydrogens dominates over the fact that the tertiary hydrogen is just slightly more reactive. And if you actually went through and calculated the percentages, you would find that in the case of bromination, the major product is a large enough percentage that's probably synthetically useful, and that you can actually identify and isolate that one product. Whereas with chlorination, right, 24 to 14 of the major product over the other products, it's probably not going to be a very productive synthetically, right? Because you'll not be able to separate these other 2 products away. Is that the part that you wanted me to go through, Katie, or did you want me to go through the mechanism as well?
Can you go through the mechanism as well, please?
I certainly can. So for any free radical chain halogenation, we're always going to have an initiation step. And that initiation step is always going to be the homolytic cleavage of the halogen-halogen bond. So one of these electrons is going to go with the bromine on the right, and the other electron is going to go to the bromine on the left to generate two bromine radicals. Homolytic cleavage means equal numbers of electrons go in each direction. And we know that the enthalpy of that reaction is equal to plus 46 kilocalories per mole. That came from table 3-4 on page 110. It's hiding in the margin notes on page 110. Right? That's not going to be part of our overall enthalpy of reaction, though, because the initiation step is not part of the balanced overall equation. There are always a minimum of 2 propagation steps. There are free radical chain mechanisms, including the one you're actually going to do in the lab, that have more than 2 propagation steps. And sometimes the initiation is not a single step. Sometimes it takes a radical is going to react with a hydrogen. And if you're showing it for the major product, you just need to show the tertiary hydrogen because that's the one that's going to be most reactive. So we're going to pluck that hydrogen off and leave a carbon radical and form the hydrogen-halogen bond. You always form the hydrogen-halogen bond first because the hydrogen-halogen bond is always stronger than the carbon-halogen bond, which means you get more energy back when you form that hydrogen-halogen bond. And I didn't ask you to do this quantitatively, but if you wanted to do it quantitatively, this costs you 96.5 kilocalories per mole to break that bond and to form this HBr bond that I think releases, if I remember correctly, I think it's 87 kilocalories per mole, being as much energy as it took. So in the second propagation step, we're going to use that intermediate. Right, so this is an intermediate because it's formed in the first step, and we're going to use it in the second step. The radical is actually a catalyst, kind of, because it's something that we're using in the first step, and then we're going to reform it in the second step. Carbon-halogen bond, and regenerate the bromine radical. So we get our product and the bromine radical. So if you want, you can cancel out the bromine radical, you can cancel out the intermediate, and the overall reaction is going to be the alkane and HBr. And if you wanted to, right, this costs you 46 kilocalories per mole to break that bromine-bromine bond, just like it did in initiation. And then you're going to get back, I believe that's minus 70 kilocalories per mole, 70 or 71-ish. Those numbers, I'm not sitting with them in front of me, so I'm not 100% confident. But what you'll notice means your overall reaction is going to be exothermic, which is why bromination is favorable. In the case of iodination, the carbon-iodine bond is not enough stronger than the iodine-iodine bond to make up for the fact that HI has a pretty weak bond. And then you should, for completeness, you should always show the termination step, something that removes radicals from the system. So one of the many possible termination steps would be a bromine radical combining with a carbon radical to generate the final product, right? And that takes 2 radicals out of the system, so it slows down propagation step 1 and propagation step 2 by removing the starting material there. That termination is constantly happening, which is why you have to shine light on it the whole time rather than just shining light on it right at the beginning and then stopping. So that's the quiz. Are there any questions? I'm going to stop the recording because it's long enough.